Hello everyone, today's topic is least square solutions. So this is probably it's the last big topic we'll consider in the class, and arguably one of the most important in terms of applications and kind of how people use linear algebra in the real world to talk about statistics and other applied disciplines. And we'll see an example of this next time, but I want to tell you the idea behind this. So what's kind of nice is that this kind of comes full circle because we're going to now come back to just solving systems of the form ax equals b, right? So this is this coefficient matrix A, b is a vector that you can think of as the right-hand side of a system, and x is the unknown. And usually, kind of in the real world, we'll say ax equals b is inconsistent, doesn't have a solution. So, again, if you're trying to find, if you're using a model of I don't know, population or other kind of economic theory, and you set up a linear equation, a system of linear equations, it's going to be inconsistent. So what you often want, what I'll give you as a definition, if A is m by n and B is in Rm, a least square solution of the system ax equals b is a vector, it's a vector x in Rn such that the length of b minus ax hat is less than or equal to b minus ax for all x in Rn. So what I'm saying here is that I don't know how to actually get something, I don't have an x that actually solves this. I don't have an x where ax actually equals b. So what I want is something that gets as close to b as possible. So what I'm saying here is that ax is as close to b as possible. Okay? So we'll make this a bit more precise in a second, but the idea here is that we can't get in general, we can't get a solution, but we want to get something that's as close as possible. And in pictures, what we're doing here, well, remember now that how do we think about ax equals b sort of geometrically? Well, we think about it as, remember, ax equals b is consistent if and only if b is in the column space of A. So what I want to think here is that, here's Rn. It's mapping over to, let's say, Rm. And remember now, the column space of A is a subspace of Rm. I'll draw it as a plane in R3 here. Now, the column space consists of vectors that give you consistent systems, right? So if ax equals b is not consistent, that means that this vector b is not in the column space. So I'm trying to draw it outside of that plane. So if it sat in the plane, then it would be giving you a consistent system which you can then solve. But it's not, okay? So what we want to do is project b onto the column space. That gives me a vector, let's say b hat, okay? But now the projection of b onto the column space, this is now a vector in the column space, which means ax equals b hat is consistent. And so that means that there is some vector, let's let x hat be a solution, right? So in general, there might be more than one, but there's going to be some vector now, x hat, where that guy is now, right, that guy maps over. So this is the matrix A that takes vectors in Rn, maps it over. Since b hat is in the column space, we know that the system ax equals b is consistent. I'm going to call x hat to be your solution, and that's what I'm talking about here. It turns out that this will be the least square solution in that sense. So what's the formula for this? Well, I'll try to have this picture here while I derive the formula. So what do we know? Well, we know that b minus b hat is orthogonal to the column space of A, because remember, this vector here is b minus b hat. And we've seen this before. This this third leg of the triangle when we project is this vector that we've used a lot, but that vector is orthogonal to the column space. You can see it's at a right angle to everything in the column space. So what does that mean? That implies that if you take AJ transpose times B minus B hat, this has got to be 0, where AJ is a column of A. So remember, the column space of A is spanned by the columns, and therefore that's a, it's a spanning set, so that means that this vector better be orthogonal to every column. Well, what does it mean to be orthogonal to a vector? It means that when I take the transpose of that vector, multiply it by the other vector, I get 0. This is the dot product of a column of A with the vector B minus B hat. And what does that mean? Well, that means that, if I take this vector AJ transpose and every one of them is orthogonal, what that tells you is that the matrix A transpose times B minus B hat is 0. Is actually the 0 vector. This is now a matrix times this vector. Every time I compute this matrix times a vector, I look at each row times this vector, I get a 0, which means that the resulting vector is a bunch of zeros, namely the 0 vector. But now what is this? AT, this is B minus, remember B hat was the same as AX hat. This is the thing that we were going for, which is the 0 vector. And now let's distribute this ATB. So this is telling you that, distributing the AT, I'm getting this equation, which finally implies that ATB equals ATA x hat. And now we're done, because what we have now is a matrix times an unknown equals a vector. Okay, so here's the theorem, is that the least squares solution of AX equals B is the set of solutions of the system ATA x hat equals ATB. Okay, so maybe it looks confusing here, but let me just emphasize what we did in this derivation is we said that what we want, this x hat, is just the solution of a system where this is your coefficient matrix and this is just a vector, right? So this is your coefficient matrix now. And this is like the right-hand side in the system. Quote unquote. Okay, so let me just do this with an example. Let me finish off with an example here. Let's see, assuming I have one. Okay, so for instance, let's find the least square solution to the system, AX equals B, where, let's say A is 4, 0, 0, 2, 1, 1, and B is the vector 2, 0, 1, 1, or 2, 0, 11, okay? Okay, so what do we need to do? Let me go back to my formula here. Okay, so, at the end of the day, we're using this formula here. What do we need to use this formula? We need to know what ATA is. So what is ATA? A transpose A just means 4, 0, 1, 0, 2, 1, right? The transpose of a matrix is take that first column, make it the first row. Second column becomes the second row. Times A, so this is 4, 0, 0, 2, 1, 1. What is the size of this matrix? This is 2 by 3 times a 3 by 2, so this will be a little 2 by 2. The first entry is what? 4 times 4 plus 1, so 17. Then I've got a 0 plus 0 plus 1, 1, and then 5. What else do I need? I need the ATB vector. So ATB will be 4, 0, 1, 0, 2, 1 times B, 2, 0, 1, 1. What is this? This should be a 2 by 1 vector, right? The first entry is 8 plus 11, which is 19. The next entry is 0 plus 11. Okay, so that's all you need. So these are the two things you need. Now we solve a system. Right, this coefficient augmented with this guy, so 17, 1, 1, 5 augmented with 19, 11. I guess I would swap rows first. Let me just save you some hassle here, and I'll tell you that this reduces to 1, 0, 0, 1, 1, 2. Okay, And so what that's telling us is that the least square solution is 1, 2. Okay? Well, okay, so we'll have more to say about this in examples, but you know, this is the idea that the least square solution is this vector. If I went back to the picture that I drew here, right? So what this is saying is that you can't really see both things on the same page here, but okay, we can try to do this. So if B is this vector 2, 0, 11, right? This vector B is 2, 0, 11. There's nothing, and A is this matrix here. There's nothing in the column space, you know, since B is not in the column space, there's nothing that I can plug in, you know, as vectors in Rn that results in mapping onto B. But I want to get as close as possible, and it turns out the thing that maps to this B hat, which is as close as possible, is this 1, 2 that I solved for. Okay? And you can actually determine what B hat is, of course. B hat is going to be A times X hat, which was 4, 0, 0, 2, 1, 1 times 1, 2. So this vector B hat, you're often interested in that. That's going to be, what is it here? It's going to be 4, 4, 3. Okay? So that's the B hat vector that I drew here. Okay, so it's in the column space just because it's of the form A times something, right? There it is, B hat, it's 4, 4, 3. And maybe last thing I want to say here is that the error associated to this is going to be the length of this red vector here. So it's going to be the length of B minus B hat, which is, in this case, the length of what was B 2, 0, 1, 1 minus 4, 4, 3. Okay, and so that's telling you how far away your vector B hat is from B. And this is going to be the length of, well, minus 2, minus 4, 8. And it turns out this is root 84, if I do that right. Okay, so again, least square solution is 1, 2. The B hat, which is the thing in the column space closest to the vector you gave me, is this one. The error associated to this least square solution is the length of that red vector, which in this case is root 84. So that's it for now. We'll talk about an application of this next time.